Okay, everyone, welcome back. So during the last lecture, the big thing that we were trying to get to and we got to right at the end was Laurent's theorem. Okay, so just to put that back on screen as is kind of my habit when starting a new lecture, right? To put the last big thing on screen here. So just to recount through this again, suppose f of z is analytic throughout an annular domain. Okay, I'll talk more about this. I'll refer to that picture that we drew last time as well. So now, suppose you have an analytic function not on an open disk, but an annulus. It's on this open annular domain. Okay, so it is, like I said, I'll look at that picture here in a second. This annular domain is centered at z0, so z0 is excluded, right, from this annular domain. Z0 and some stuff around it. And let C be any positively oriented simple closed contour around Z0 lying entirely in that annular region. Okay, so just to flash this picture on the screen for you real quick. There's what it looks like, right? There we go. Okay. And so, at each point in this domain, the purpose of this setup is to say that where we talked about the existence of a Taylor series for an analytic function on an open disk, now we're talking about an expansion that is not quite a Taylor series, right? Or it's not quite a power series. It would be if this term didn't exist. Okay, but we have a series representation. So note I didn't say power series representation here because this is not a power series. Okay, but we have a series representation for this analytic function on this annular domain that is of this form. Okay, and so this is one way of writing it. So I have all of the positive indices here, right? All the positive powers of z together with coefficients, plus another sum that's all the negative powers of z, right? So if I rewrote this by changing the indices here to sum across negative integers, then what I would get here is this is like a power series involving the negative powers, okay? Which is, not the definition of a power series, but it's, it's a kind of power series, right? It's a power series involving negative powers. Okay, so we have this thing where, and this is a very important thing, these coefficients are actually determined by the Cauchy integral formula, and it looks exactly like this. So that's where this contour C in my annular region comes in. I can actually compute these coefficients using Cauchy integral formula, basically the contour integral here around this C, and it's done in this way. Okay, so very familiar expressions there. Okay, this series is called a Laurent series, okay, and this is called Laurent's theorem. So Laurent's theorem concerns the existence of a Laurent series for an analytic function on one of these annular domains. Now, as we saw when I first introduced this, through a little bit of algebraic rewriting, I can write this in a slightly more compact form that's more convenient a lot of times to deal with. So this is what that looks like. So if I do exactly what I mentioned before, if I actually replace n by minus n, okay, and so I view this as this is a b sub minus n here, right? If I was using LaTeX, I would have brackets around that thing. Okay, so this is b sub minus n here, and I'm summing over the negative powers of z here, right? So combining this with my other series, I can write these together as a sum from n equals minus infinity to infinity, where I've bundled my coefficients together, right? And of course, I could even relabel these as a sub minus n, right? I could actually use the same letter here if I really wanted to. But here, this is one single bundle containing all of these coefficients here, summing from minus infinity to infinity. This is a more compact way, and typically this is the way you'll see Laurent's theorem stated. And this is, in a lot of cases, this is how you're going to see a general Laurent series written out. Okay, so when you see something like this, this is a Laurent series generally. Now, if all of these C sub n's that correspond to the negative powers are 0, then this is a power series, right? So note, like if all of these B sub minus n's are 0, then what I'm left with are just the coefficients on the positive powers of this series. And so what I'm left with is actually just a power series, okay? And so if I write a general Laurent series, right, if it's an actual honest-to-God Laurent series, it needs at least one non-zero coefficient for one of the negative powers. Okay, and I still have this formula, and this comes from the statement of Lorentz theorem. Similar to what we did with Taylor's theorem, the proof of Lorentz theorem is actually not going to be too terribly useful going forward. We're not going to apply anything directly from the proof. And it is actually proved in kind of a similar way. Basically, you first show this for an annular region centered at 0, and then it's hardly any work at all to show it for a general annular region centered at some z0. Okay, and so you can have a look at the proof if you want to in the textbook, but I'm actually not going to go through the proof of that. And this is called the Laurent series expansion of f of z about z0. Okay, so Lorentz theorem guarantees the existence of this if such a function is analytic on this annular domain. Now, let's go back, as I promised, to this annular domain, have a look at it. So what is the deal here? What's the idea? I've drawn an annular domain. Why am I talking about a function on an annular domain when up till now I was basically talking about functions on disks, right? Open disks. So the idea here actually is note. Well, I say note like you can actually notice this, but maybe I should just write this as a fact. It actually doesn't matter how much of the middle is excised. I was writing it like that. I.e., my annular region could look like this, right? So my annular region could be, say, here's the outer boundary, and the inner boundary is like this. All right, so there's z0, right in there. There's some inner boundary. It's tiny, you can't even hardly see it, and then there's an outer bit. Okay, i.e. my annular region could actually be a punctured disk. That's fine. Okay, so actually it's absolutely fine. This is a punctured disk. Okay, so what I'm saying here is that the more common thing to happen, right? Like if you view this as it's a region on which the function you're given is analytic, right? So I'm going to highlight the two boundaries in red here. Okay, maybe you are dealing with a function that is literally only analytic on this annulus, right? But that's not typical. That's not what you're going to be dealing with typically. Typically, in the context where you want to talk about this stuff, you're going to be talking about a function that's analytic pretty much everywhere except at some finite number of points. Okay, and say that we're dealing with a function that's analytic everywhere except at this one point. Okay, well, what I'm saying is that if f of z fails to be analytic at z0, right, but is analytic everywhere else in the larger disk, the outer disk, right, but is, oh, that is not how you spell analytic, but is analytic everywhere else on the open disk, which is disk centered at z0 of radius r sub 2. I think we used r sub 1 and r sub 2 in our statement of of Lorentz theorem. Yep, just to make ourselves sure. Yep, that's exactly what we did. Okay. What this means, so if I have an f that is analytic actually everywhere on the, so it's actually analytic absolutely everywhere here except at z0, right? That is the only problem point. Okay. What I'm saying is that this inner radius can be made arbitrarily small. This can be made arbitrarily small. And so what you're actually dealing with is like a punctured disk. Okay. All right. Okay. All right. What about the other case, right? What about the case of it is analytic everywhere, say like exterior to uh, uh, say it's analytic everywhere exterior to the inner circle. Okay, then so suppose f is analytic everywhere exterior to the inner circle. Okay, then the condition of validity, which is the condition where we have a Laurent series, is this one. So this condition guarantees a Laurent series of f. Add z naught. Okay. Okay. Now, if you have this statement that it's actually analytic everywhere except at z naught, then you can actually get this for just the punctured plane, right? If f is analytic everywhere. Everywhere in C except z naught, then the condition is the punctured plane. All right, what is that condition? Everything is fine except z naught. Right, there's a hole at z naught, but everything else is fine. Okay, and so we would have a Laurent series that has, a condition of validity, right, where this function is actually equal to its Laurent series everywhere, right, except, so that thing would be analytic everywhere except at z naught. Okay. All right, so going to bring back the statement of Laurent's theorem real quick. Whether you're using the compact form of it or the other form involving a sub n and b sub n, let's just look at the compact form for now. So here we go. You might say that if I wanted you to actually seek out a Laurent series, well, it's going to require computing these contour integrals, right? So on one hand, the fact that Laurent's theorem tells you that these coefficients are given by computing these contour integrals is really, really nice. We're going to see a lot of examples showing exactly how nice that is. On the other hand, it wouldn't be that great that for every single coefficient in that series, right, you have to compute a contour integral because, well, there's infinitely many of them, right? And so if there's not really a nice systematic way of doing that, that could be really, really, really annoying. And so that is not ideally, in practice, this is actually not how we're going to find a Laurent series. We're not going to find them by computing a ton of contour integrals. So in general, to find a Laurent series expansion of some function f of z, we use known facts about certain Taylor series and other series. Taylor series slash other functions. Okay. So to show you how this works, right? Suppose I want to find the Laurent series expansion of e to the 1 over z. So find the Laurent series expansion of f of z, which is e to the 1 over z. Say this would be, Laurent series representation, about 0, right? So Laurent series expansion about z not equals 0 of this function. Okay. All right, how do I do that? So first of all, this function, what's the deal with this thing? Where is it analytic? So you might remember you've actually dealt with this example a couple times. I think we did it in a lecture, and it was also on a homework at least once. what is this? What's the deal with this function? E to the 1 over z is analytic everywhere except at 0, right? And so the condition of validity that we're going to be looking at is going to be something like this, right? So the Laurent series we're going to be finding had better be valid here. Now, how do I find the Laurent series for this thing? I'm not going to write out contour integrals, like I said, right? That's the hint. What I want to do is I want to use the Taylor series expansion, or in this case, since we're expanding about z not equals 0, I'm going to use the Maclaurin series for e to the z, and then just replace z with 1 over z, right? So recall, e to the z has our favorite Maclaurin series expansion. So e to the z is the sum from n equals 0 to infinity of z to the n over n factorial, which I can write out, this is 1 plus z over 1 factorial plus z squared over 2 factorial, and so on. Okay, so then e to the 1 over z, if I just formally replace z by 1 over z here, what do I get? This is going to be the sum from n equals 0 to infinity of 1 over n factorial times z to the n. So here, of course, the z's are in the denominator, right? So this is, just writing this out, this is 1 plus 1 over 1 factorial times z plus 1 over 2 factorial times z squared, and so on. Okay, and this is indeed valid everywhere in this the domain described by this, right? This, which is just the punctured complex plane where the origin is removed. Okay. So, what can I say here? So, first of all, there is a fact that I'm going to state later, but I'm going to go ahead and mention it now, just because it's eminently mentionable. Is the fact that suppose that you cook up a series expression or a series representation for a function that involves these negative powers of z, and so it would be a series of the Laurent type. Okay, and you show that it's equal to that function on some domain. Is it actually the same as the Laurent series for that function on that domain? The answer is yes. The answer is yes, because and this fact is not just true for Laurent series, it's also true for Taylor series, because Laurent series and Taylor series are unique, okay, on the relevant domains. So that means if you find another power series expansion, like another power series expression for a function on some given domain, that thing has to be its Taylor series. Okay, so we actually made use of that already in some of the stuff that we did. The same thing is true for Laurent series. So it has to be its Laurent series, and so this thing actually has to be the Laurent series because it's of that same form. Okay, note, right, that directly from this, if this is my Laurent series for e to the 1 over z, note, by my own, where's my theorem that is written in the non-compact form? There it is. So if I think of this as split up into two parts, right, the sum that sums over the positive powers and the sum that sums over the negative powers, and so my positive power coefficients are a sub n and my negative power coefficients are b sub n. Okay, well, looking at this, actually, I have a really easy way of computing all of these b sub n. So note, first of all, right, this has infinitely many non-zero b sub n's. What are b sub n's? B sub n's are the coefficients on the negative powers, right? So this is us saying that there are infinitely many negative powers in the Laurent series expansion for e to the 1 over z. Okay, that is an example of a thing that I'm not going to write it out now. because I'm not going to bother defining it now, and I don't want any confusion when you're looking back through and you see it, but then I don't define it. But this is an example of something called an essential singularity. So back in like the third office hours we did, I think, I was asked by a student for an example of a function. I think it was a function that satisfied Cauchy-Riemann on some domain. And that was the only condition that it had. Maybe like one more thing, but it wasn't analytic. And one of the examples the example that I gave that I didn't cook up myself, I had to look it up. One of the reasons why it fails to be is because it has this essential singularity. And I said like this thing has an essential singularity, but then I kind of had to stop and defer to later because I hadn't talked about essential singularities yet. I still am not going to define it now. We're going to do that next. That's going to be like Monday's lecture. And so this having infinitely many non-zero coefficients on these negative powers is a like really naughty thing. This is like a bad property that a function can have. What it means is that it's a type of singularity that is not the behavior of the function is not predictable near a singularity like this. Okay, and that's what essential singularity means. Literally, it means that exactly this. This is infinitely many non-zero coefficients in the Laurent series on the negative powers. Okay, but specifically, right? These are actually easy. I can just pick them out. So, for instance, this is b sub 0, z to the 0, right? This is b sub 0 times z to the minus 1, or sorry, not b sub 0, b sub 1. So b sub 1 here is just 1 over 1 factorial, which is 1. 1 over 1 factorial, which is 1. Okay. But using Laurent's theorem, let's go back. So I've shown just by literally writing out this series and saying, look, there's the b sub 1 term, right? And b sub 1 here is just 1, right? There it is. I can just see that it's 1 here, okay? But I know that these b sub n's can be computed by this contour integral. So these b sub 1's can be computed by this contour integral. So what does that mean? That means by Laurent's theorem, let me bring back that sheet real quick. So by Laurent's theorem, I know that another way of writing b sub 1 is as 1 over 2 pi I of the contour integral of f of z. Here f of z was e to the 1 over z. So this is e to the 1 over z over z naught is 0, so this is z to the n here was 1, so this is minus 1 plus 1 dz. So this is 1 over 2 pi I times the contour integral of e to the 1 over z dz. But I know that this is 1. And so, multiplying both sides by 2 pi I get that the contour integral of e to the 1 over z dz over any c that is that circles the origin, right? Where c is any closed contour, where c is any simple closed contour, that all it has to do to be in this annular region, right? This is a fake annular region. This annular region is just a stupid punctured plane, right? Where the origin is removed. So all this thing has to do to be in that region is to circle the origin. So where C is any simple closed contour that circles the origin. So it must go around the origin. This is multiplying by 2 pi I here times 1. This is just 2 pi I. What? So Laurent's theorem gave us a way of computing this. How would you compute this otherwise? Right? Now, how would you compute this? So Laurent's theorem gave us a sneaky way of computing this, right? So in fact, just from this process, Laurent's theorem Why did I put the apostrophe there? Laurent's theorem gave us a sneaky way of computing a non-standard contour integral, we'll say. I don't know if I want to call it non-standard because you're going to be doing this kind of thing a lot, but for now it's non-standard. This is our first example of the residue theorem. Okay, so here's my aside. This is our first example of the residue theorem. Where does the name come from? The name comes from the coefficient b sub 1, or written in the other form, this would be c sub minus 1, right? Which is called the residue. It's called the residue of f of z at, in this case, z naught equals 0. Okay, but this can be totally general. So this is called the residue theorem. This fact is called I should say it's a special case, the residue theorem. Okay. So the residue theorem is basically going to pop straight out of Laurent's theorem, and it's going to be really awesome because it is going to give us maximum tools for computing some really, really crazy integrals. And the hope is that I will get to the residue theorem on Monday and spend the rest of the lectures basically doing applications of the residue theorem so you can just see how awesome it is. That's the goal, okay? And you're going to see even, hopefully, how we can apply it to areas you would not think that it would apply to. Okay, because, we're in the realm of complex analysis, right? How can you use this to compute some real integral, some crazy, like, improper integral in the reals or something? How could you do that? Well, you're going to see exactly how we're going to do that, okay, using the residue theorem. Okay. So let's do another example. So we're gonna do a ton of examples like this. That was a good one. Okay, to spend a decent amount of time on. So let's do another example here. Pick the function 1 over z minus I all squared. Okay. Well, this is already a Laurent series. Okay, this is already a Laurent series. What is it a Laurent series of? It is a Laurent series of f of z, which is this is a Laurent series of so this is, maybe I'll actually just write out the Laurent series directly here. I won't even write out an f. So to see this as a Laurent series, let z naught be equal to I. Okay, then 1 over z minus I squared is equal to the sum from, say, n is equal to minus infinity to infinity of c sub n times z minus I to the n. Okay, where c sub n is equal to 0 if n is not minus 2. Right, and c sub n is equal to c sub n c sub n is equal to just 1, right? If n is equal to minus 2, right? I.e., c sub minus 2 is equal to 1, and all other c sub n is equal to 0. Okay, that's just me writing this out. Okay, but by Laurent's theorem, the fact that we have used this expression to notice, oh, this is already in the form of a Laurent series, and here's the coefficients. Laurent's theorem tells me that these coefficients have to be computed by these contour integrals. All right, let me bring back the compact form. Why do I keep losing it? Here we go. All right, so these c sub n's have to also be able to be computed by, there we are, right? And so, what does this tell me? Well, these c sub n's then have to be computed as 1 over 2 pi I of the contour integral of, in this case, my f is actually just 1 over z minus I squared. And so what is this? The statement here is that this is f of z over z minus z naught to the m plus first. So this is going to be, because f is 1 over z minus I squared, this is going to be 1 over z minus I to the n plus 3, right? dz is the integrand. Okay. But the fact that c sub n is also just 0 for everything except when n is equal to minus 2, what does this mean? It means that another way I can write this is by multiplying by 2 pi I here, this integral, right, over contour c. C is going to be a contour that circles I here, right? So c, where c is a contour that goes around I. Now, it doesn't, does it have to actually be a circle centered at I? Of course not, right? That's just a very easy example of that. But you could, as long as you have any, well, I said it's a contour, but it's a simple closed contour. All right, so C is a simple closed contour that circles around or goes around this point we're using the Laurent series expansion about. Okay, that was part of it, right? C had to be in that annulus. Here, though, we're specifically talking about a thing that is again a punctured plane here. So this is, first of all, where is this valid, right? I didn't write my validity condition here. Shame on me, right? But this is valid exactly where you think it is in the punctured plane where I've removed z. Z equals I, right? So I've removed I here. Okay, so everything is there in the plane except I on the positive y-axis. So then this contour integral now, using Laurent's theorem backwards, right, is this is the contour integral over the c of z minus I to the m plus 3 dz. This is equal to, well, it's equal to 0 if n is not equal to minus 2. And it is equal to 2 pi I when n is equal to minus 2. And so I just quickly computed a nice class of contour integrals in this way by using Laurent's theorem. Okay. So that's another nice example. Let's do one more very instructive example because it's actually going to be like 3 examples rolled in one. Okay, so here's one more. Okay, so let f of z be the function that is minus 1 over z minus 1 times z minus 2. Okay, so I can actually write this, if you like, as 1 over z minus 1 minus 1 over z minus 2. Okay. So note z equals 1 and z equals 2 are two singular points of f. Okay. And f is analytic in the domains that are inside. So like, say, the open unit disk, the annular region, right, between the open unit disk and the open disk of radius 2, and then the region exterior to the open disk of radius 2. So if I call this domain d sub 1, and I call this domain d sub 2, and this domain d sub 3, there's an easy way of drawing a picture showing all these domains. So d sub 1, of course, is everything inside this, so maybe I'll use red here. So here's d sub 1. And d sub 2 is everything inside this annulus here. I'll use blue and I'll go the other way. There's d sub 2. And then d sub 3 is everything exterior, and I'll use black for that. Alright, so d sub 3 is everything else, which I won't shade in as aggressively. Okay, so I have split my plane in this way. I have two singular points, right? Here's one of them. Here's the other. Okay, they are excluded in this way that I have split. Okay, now what I want to do is I want to find some type of series representation for this same f on each domain separately. Okay. Okay. Well, I'm viewing f of z as just being, the difference between two things that look like this, right? Well, things that look like this, I already know what some power series for these things look like, right? So I know, so recall, for instance, that, right, this was like one of the first things we did, was for geometric series, 1 over 1 minus z, that could be written as the sum from n equals 0 to infinity of z to the n, right? The geometric series, if modulus of z was strictly less than 1. Right, we could do that. So this is like one of our first examples. Okay, so recall this. All right, so let's do D1 first. So start with D1. So on D1, that's this inner open disk. What kind of series representation? This is the thing that I want to do here. Maybe I should box this. All right, so what kind of series representation am I going to find in D1? So in D1, I have it's analytic on everything in this open disk here. This, think for a second, this should have a Taylor series, right? In fact, let's say compute the Maclaurin series, right? That is Taylor series around z not equals 0. Right, so note on D1, f of z has a Maclaurin series representation. I feel like this t shouldn't be there. So f of z has a Maclaurin series representation. How do I see that? So note on D1, modulus of z is strictly less than 1. Let's bring back our picture real quick. So D1 is this domain. Here we go. Of course, and modulus of z over 2 is also strictly less than 1. Why does that matter? Well, we can actually rewrite f of z here. So f of z we wrote as 1 over z minus 1 minus 1 over z minus 2. Right, that was how we could write that thing. So I'm going to rewrite this as 1 over 1 minus z, minus 1 over 1 minus z plus 1 half times 1 over 1 minus z over 2. So that I can use this, I'll box this in red. My idea here, of course, is to use this very convenient Taylor series expansion or Maclaurin series expansion for the geometric series, right? And I'm going to substitute the z that I'm putting in here, right? And I can do this so long as the quantity has modulus strictly less than 1. So that's why I checked and noted, oh, well, of course, z has modulus strictly less than 1, but also, if I'm on D1, z over 2 has modulus strictly less than 1. And so, writing f in this fashion, f of z, using that expansion I just boxed in red, right, there we go, using that in both places here, what is that going to be? This is going to be minus the sum from n equals 0 to infinity of z to the n. It's just directly using Maclaurin series expansion for that thing. Plus 1 half times Maclaurin series expansion for 1 over 1 minus z over 2. I can just plug z over 2 in to the Maclaurin series expansion for 1 over 1 minus z because z over 2 also has modulus strictly less than 1. And so this becomes plus the sum from n equals 0 to infinity of z to the n here over 2 to the n times another 2 in the denominator here. So this is over 2 to the n plus 1. Okay, and so rewriting this slightly, this is the sum from n equals 0 to infinity of 2 to the minus n minus 1 minus 1 times z to the n, combining those. Okay, and this is valid for modulus of z strictly less than 1. So we have found on D1 a Maclaurin series expansion. There it is. All right, that is a Taylor series expansion about 0. Okay. What about on D2? So on D sub 2, how am I going to handle this? On D sub 2, note, let's recall, what does that domain look like? So D sub 2 is this annular region. So there it is. So modulus of z is strictly between 1 and 2. So what do I know here? Well, this means that the modulus of 1 over z is strictly less than 1. That's one thing that it means. And also, the modulus of z over 2 is strictly less than 1. Hey, how's this going to help us? Well, now I can rewrite f in a slightly different way. Okay, this is a lot of algebra trickery. Right, so rewriting f in a slightly different way here. Now I want a 1 over z to pop out here somewhere where it should. So I want to plug in 1 over z in for z in my Maclaurin series expansion for the geometric series. So then I factor z out of the denominator here, so this would be 1 over z times 1 over 1 minus 1 over z. So there's that. Right, plus the same thing I did before, 1 half times 1 over 1 minus z over 2. So now you're understanding why I'm writing f in the same way. All right? So what does this tell me? So then this tells me that f of z can be written as, so now I'm using, I'm thinking of this as, this is 1 over z times 1 over 1 minus 1 over z. So if I use the geometric series for this, I'm also dividing by z here, right? This is the sum, trying from n equals 0 to infinity of, it would be 1 over z to the n, but because I'm multiplying also by 1 over z, this is 1 over z to the n plus 1. All right. Plus the sum from n equals 0 to infinity of the exact same piece that I got last time, which is z to the n over 2 to the n plus 1. Notice how this thing looks. So first of all, what is the domain of validity? Right, it's D2. Okay, what is this? Right. Well, this is actually a Laurent series expansion, but you might say, wait, both of these start at n equals 0 here. Right? Well, I can write this in another way. So here's a way, and this is just kind of reminding you of some Calc 2. This is kind of some of the stuff you did when you were first introduced to sigma notation, right? Is that you can actually recast this slightly so that we can put it in exactly the form of a Laurent series expansion. What do I want to do? So here, I can swap the index, right? So I can swap the index here, and instead of using n, I can sum by n minus 1, and then I can just swap the series around here. So for instance, I can rewrite this as f of z is the sum from n equals 0 to infinity of z to the n over 2 to the n plus 1, so that's still fine. Okay, plus if I'm now do an index shift where my index is now n minus 1 instead of n, right? Then what happens is that this series shifts and now starts at n equals 1 to infinity, and this is 1 over z to the n, right? Purely from just shifting the index. And so now this is exactly a Laurent series, right? So this is a Laurent series representation for f. This is the Laurent series representation for f on this domain d sub 2. Okay. All right. As I mentioned previously, since I'm going to state here in another few minutes this fact that Laurent series are unique, which means that if you can find any series that is equal to f on an annular domain, right, that looks like a Laurent series, it is actually the Laurent series, okay, of f on that domain. All right, so Laurent series are unique in that way. Let's do the last thing here. So on D3, what is the expansion? Again, let's go back to our picture. D3 is the domain that is exterior to the circle, the open circle radius 2. So it's exterior to that. It's all this stuff out here. So this is my domain here, right? So D3. So the modulus of z is strictly between 2 and infinity. Okay. So how does that help me? Well, one, note here I have that the modulus of 2 over z is strictly less than 1. But if that's the case, right, then the modulus of 1 over z is also strictly less than 1. Okay. And so now I can rewrite my f yet again. Let's even remember what my f was. Right, there's my f. So let's rewrite it in its original form. 1 over z minus 1 minus 1 over z minus 2. So I want to rewrite this so that I can make use of these two facts instead now. And so what I do here is I can factor out now by a 1/2 and a I can factor out by a 1 over z, and that's 1 over z times 1 over 1 minus 1 over z. Okay, and I'm subtracting from that 1 over z times 1 over 1 minus 2 over z. And that's all I need. Both of these things I'm going to plug into that Maclaurin series for the geometric series thing. Those are fine because their moduluses are both strictly less than 1. And so f of z can be written as, just as before, this becomes the sum from n equals 0 to infinity of 1 over z to the n plus 1, okay, which we know we can rescale in a nice way if we needed to here. But actually, the second sum is the sum from n equals 0 to infinity of, now there's a 2 here, and so this is 2 to the n over, you get an extra copy of z in the denominator, so this is z to the n plus 1. Okay, since I know these things actually converge everywhere I care about, I can do this difference no problem. So this is the sum from n equals 0 to infinity of 1 minus 2 to the n over z to the n plus 1, and this is on the domain D3, right, on D3. I'm not going to rewrite it. So that's what it looks like. Okay, of course I can actually reshift this. So reshifting this, f of z is the sum, so again replacing n by n minus 1 here. This is the sum from n equals 1 to infinity of 1 minus 2 to the n minus 1 over z to the n. Yeah, that's right. And this is for modulus of z is strictly between 2 and infinity. And the reason, again, that I wanted to put it specifically exactly in this form is that this is, again, a Lorentz. This is a Lorentz series with all of the a sub n's equal to 0 for all n, and b sub n is equal to 1 minus 2 to the n minus 1, right, for all n. So the coefficients here on its positive powers of z are all 0, and the coefficients on its negative powers of z, well, there they are, right? Because this thing only has, its only non-zero coefficients are the ones on the negative powers. Okay, so this kind of gives you a nice taste for the kind of stuff that's going on here. All right. Okay. Continuing along. Now we want to talk about a bunch of nice properties. Okay, so now we want to present many nice facts about Taylor and Laurent series associated to analytic functions on relevant domains. And we will present these without proof. Because what is important to us is actually how we're going to use all these facts to basically be able to say that what we're doing is it works out nicely when you're dealing with these situations that we've set up, right, in the statements of these theorems, Taylor's theorem and Laurent's theorem. Okay. All right, and so what is the first thing that I want to talk about? So the first involves absolute convergence and uniform convergence. So absolute convergence you know about. You might not know about uniform convergence. Okay, so let's break these down first of all. So this is absolute and uniform convergence of power series. So what does absolute convergence mean? So a series absolutely converges if the series of absolute values converges, right? So so a sum of complex numbers here. This could be a power series. It could be any kind of series. Okay. So here's my series. This is my series, then it converges absolutely if so this converges absolutely if the same series where you have replaced this with the modulus of the coefficients converges. This is stronger than normal convergence because if you have a sequence, or if you have a series that converges absolutely, then it automatically converges normally. And that's just about the simplest possible inequality you can imagine. What do you think is the relationship between a series like this and a series like that? Right? Of course, this one dominates it. So if this thing converges, right, then this thing's sequence of partial sums have to. There's no possibility here. And if this thing converges, then this sum is equal to some finite value, and so this thing converges. Well, I should be careful here. I should be careful. This is true if we're dealing with positive series. Okay. So if we're dealing with positive series there, that's true. Some of these statements are a little bit trickier if you're not dealing with something like that. But regardless, absolute convergence is a stronger condition. Okay, that is true. Okay, and so this thing converges absolutely. That's exactly what it means, what I boxed here. Uniform convergence is a little bit trickier. So the way that uniform convergence works, this is a uniform convergence power series. Basically, it's that the definition of convergence of a power series normally, right? Let rho let rho sub n of z be the remainder, okay, of a power series, and we'll call the power series a big S of z. Okay. Now, what do we know? We know that if S of z converges, then this rho sub n of z must limit to 0. Okay, as big N goes to infinity. But the definition of this thing limiting to 0 as big N goes to infinity means that this remainder term, its modulus is strictly less than epsilon if n is larger, right, than some chosen n sub epsilon z, I will call it, okay, where the chosen big N sub epsilon z is sufficiently large. Okay, so this ended up being a long-winded description that I meant to go into, but that's fine. It's kind of necessary to see this. So this is just the definition of converging to 0. Typically, the way that convergence to 0 works, when you're dealing with something that has an argument here, then there is dependence. This n depends not only on epsilon, right? So the statement, right, is that for every epsilon, what is said here is that for every epsilon greater than 0, there exists a big N sub epsilon z such that this is true. Now, the reason I'm writing that there's a sub epsilon z here is that typically the way that this convergence works is that the big N that you're thinking about is something that typically depends on the epsilon chosen and the z chosen. Okay? So the entire purpose of uniform convergence is that there is no dependence on the z. Okay, so that this n sub epsilon depends only on epsilon. Why is that called uniform convergence? If it depends only on epsilon, it means it doesn't depend on the point in question. Okay, and so this convergence happens in a nicer way. All right, now it's not our goal in this class to kind of like investigate all of the I should say like ramifications of of all of these like analysis theorems and stuff. That we're not like that's not what we're going to do here, but this is something that still you should know. But intuitively, right? We basically only care about kind of intuitively understanding what's going on with this stuff because we're just going to apply these facts. Okay, and so this is the deal. Okay, and so what are the theorems in question? So first theorem: if a power series that I will write as the sum from n equals 0 to infinity of a sub n times, say, z minus z naught to the n converges when z is equal to z sub 1. Okay, and they're not equal, so we'll say z naught is not equal to z sub 1. Okay, then it is absolutely convergent at each point z in the open disk, that is modulus of z minus z naught is strictly less than r sub 1, where r sub 1 is the distance between z1 and z naught. Okay. So in the picture here, you have the expansion, right? Your power series is expanded about z naught, right? The disk that you're talking about here is a disk of radius r sub 1. This is the distance from z naught to z sub 1, which is a point where this power series converges. And so what we have here is convergence for every point z, say, belonging to that open disk. Okay, so we have absolute convergence of series for that. Now, why do we care about absolute convergence of series? Absolute convergence of series tells you that some of the funkier stuff that happens with series when you want to deal with them algebraically doesn't happen. Okay, and so the big things that we're going to pop out of this are that we can treat series algebraically in kind of the best way we can expect. So if you have a power series, it can be differentiated or integrated term by term. Okay, that's a great thing. That's a great computational thing that you're allowed to do for then any function that has, say, a power series representation. Right, so that's nice. And it's not just that. It's basically all of the operations that you want to do on power series works out nicely in this case. Okay, now we need a definition here before I can state the next theorem. So quick definition. Okay, and in fact, another way of even phrasing this theorem is in terms of this definition. So what's the definition? This is the definition of the circle of convergence. What is a circle of convergence? This is the greatest circle. So the greatest circle centered at z naught such that the series above converges at each point in the interior is called the circle of convergence. Of the series. Okay. So it can't converge to any point outside the circle, right, by this theorem, because if it did, then it would converge everywhere inside the circle and passing through that point. Okay, and so then the first circle that we started with would not be considered the circle of convergence. Okay. So what does this theorem say? This theorem says that the set of all points inside some circle centered at z0 is a region of convergence for the power series listed here, provided that it converges at some point other than z0. Okay. All right, so that's the point. If you have convergence at any other point, then you have convergence on neighborhood, right? You have a circle of convergence, okay, for this thing. All right. And so I defined this this notion of uniform convergence. Maybe I'll expand it a bit. So I already wrote down the definition, but let's say that we have a power series, and I write that as S of z is the sum from n equals 0 to infinity of a sub n times z minus z naught to the n. The power series, right, up to big N, right, is this truncation. So it's actually a polynomial. So this is the sum from n equals 0 up to big N minus 1 of a sub n times z minus z naught to the n. So you know exactly what that thing is. We'll say that our defining, right, our region of validity here is open disk of radius big R, centered at z naught. This remainder function that I wrote before, this rho sub n of z, is just the sum, or sorry, the difference of the entire power series, where I've subtracted off its first n minus first terms. Right, so that's exactly what that difference is. And so, since we know that the power series converges, this thing has to converge to 0, because if the power series converges on this region, then by definition, right, note that the sequence of partial sums is actually just given by exactly this thing here. So the limit as big N goes to infinity of S sub big N of z is actually equal to S of z. And what this means is that since this thing then has to be the limit, right, point-wise, right, per z here, this thing has to go to 0, right? So we know that just like we knew that before I even stated the definition of and this is if S of z is convergent. Okay, and so we know that this remainder has to limit to 0, and that's before I even stated the definition of uniform continuity, or sorry, uniform convergence. So this convergence is called uniform in that way if this thing goes to 0 in a way where the chosen big sub n that depends on epsilon and z doesn't actually depend on the point in question, then it's called uniform convergence. And the theorem that we have about this fact is the following: if z sub 1 is a point inside the circle of convergence, we'll say the circle of convergence, we'll just call it exactly this circle of radius r centered at z naught of a power series. So I'll use the same exact notation here. Okay. So z1 is a point inside the circle of convergence of a power series. Then that series must be uniformly convergent in the closed disk. So not just on the circle. In the closed disk, that is closed disk of radius r centered at z naught. Okay. Or sorry, of radius r sub 1, where r sub 1 is the distance between z sub 1 and z naught. So same kind of picture as last time. Okay. So why is this nice? Again, these two theorems, you are not frequently going to apply them kind of on their own. We are going to use the things that these things imply. Okay, so there are theorems that are implied by these two theorems that are going to make us happy in dealing with these power series. Okay, and so for instance, sums of power series and continuity of sums of power series are something that we get out of it. And so one consequence of these is the following. So we have a theorem which says that the power series represents a continuous function at each point inside its circle of convergence. So this represents a continuous function s of z inside its radius of convergence. Sorry, it's a circle of convergence. Which is, again, the circle, we'll call its radius r here. Okay. All right. And so this is an immediate consequence of that fact about uniform continuity that I just wrote down. Okay. This can also be applied to Laurent series. Not just power series. So how do I see that? Okay. Well, then, so there's another theorem. So if a Laurent series let's say a Laurent series representation, I'll write it as f of z is some, so the power series part, right, plus the negative powers part, sum from n equals 1 to infinity, of b sub n over z minus z naught to the n. Right, so if a power series representation is valid in some annulus, then both of these series converge uniformly in any closed annulus which is concentric to and interior to that region. Okay, then both of these series converge uniformly in any closed annulus. Concentric to and interior to that region. So concentric and interior to that region. Okay. Okay. Okay, we're getting to where we want. All right, now notice, like, I'm not proving any of these, I'm just stating them. We're about to get to what we really care about from some of this stuff. So the next thing is application to term by term differentiation and integration of power series. So how does this help me? Well, if a power series represents a continuous function at every point interior to its circle of convergence, the question is, let's think backwards for a second, right? So we've shown that a power series is continuous at each point interior to its circle of convergence, but in a way this isn't as good as we expect it to be, right? Because we actually know, right, like Taylor's theorem tells us that if we have an analytic function, which is stronger than continuous, we have an analytic function, then Taylor's theorem literally says that it has a power series expansion, in some domain that we care about. And this power series expansion, right, that the fact that we say it has a power series expansion, what that means is that on that domain, it is equal to that function, right? It converges to that function's values. And so that function is equal to that power series on that domain. And since the function is analytic, then we would expect the power series to be analytic, right? At least like a lot of the time, because just going forward from Taylor's theorem, right? We start with an analytic function, we find that it has a power series expansion. That power series then is analytic. So then the question is, are power series, right, like that are these supposedly really nice objects we're interested in, they inherently analytic on, the obvious domains? And the answer is yes. Okay, so the fact that they're continuous is one thing, but it turns out they're actually analytic within that circle of convergence. And to show this, first we will use a theorem on integrating term by term here. Okay, so theorem, if C is any contour interior to the circle of convergence, this is any contour interior to the circle of convergence of the power series that I keep having to rewrite. We'll say it's sum from n equals 0 to infinity of a sub n times z minus z naught to the n, right? And if g of z is any continuous function on C, then I can integrate the power series formed by multiplying the above power series by g of z term by term. And in fact, I'm doing this integral over C. So before, when we did term by term integration differentiation of power series, you were just using calc 1 derivatives and calc 1 integrals here. So our analog of that, of course, is contour integrals. So here I'm integrating over contour g of z times, we called it s of z, right, dz, which is this sum. And I'm claiming that I can actually break this up as the sum from n equals 0 to infinity of a sub n times the contour integral over c of g of z times z minus z naught to the n dz, right? So here's how I can do that term by term integration. Okay, so I can pull an integral through an infinite sum, right? This is the key. This is when you say you can do term by term integration, you're saying you can pull an integral through an infinite sum. You know you can pull an integral through a finite sum because integrals are linear. But there's some argumentation that has to go into showing you can do that in the case that the sum in question is infinite, right? Because there's always things that have to be nailed down to make sure no pathological stuff happens. Okay, now this theorem is nice. It's always really nice to be able to do term-by-term integration of power series in this way. But note that actually you might say, well, actually, I just want to integrate the power series itself. I don't care about multiplying it by function and doing it. And that's good. That's a good instinct. Because what happens if we let our function just be equal to 1? Right, so note, pick g of z identically equal to 1. Right, pick g of z identically equal to 1. Right, and we'll pick g of z identically equal to 1 on whatever the relevant region we're talking about here. So this is our region that lies inside the circle of convergence, right? So this is what we're talking about. Okay. So what happens when I let this g of z be identically equal to 1 there? Well, in this formula, right, this becomes the integral over c of g of z times s of z dz. So g of z is 1, so this is the integral over this contour of z minus z naught to the n. Right? This is some simple closed. I mean, it's a contour interior to circle convergence. Circle convergence is a circle, so this is on a simply connected domain, right? So you're integrating this analytic thing on a simply connected domain. This is definitely 0. Okay, so that's 0. Doesn't matter what n is. That's always 0. I don't have to say anything. Actually, I don't even have to say anything about n. This is just always 0. Okay, and this is actually 0 for every c, right? For every closed contour. So this is true for every closed contour c, okay, that lies in that domain. Okay, and what this means, of course, since I've taken g of z to be 1, this is telling me that the integral over every such c of s of z dz is equal to 0, right, for every such closed contour. What does that tell me? Right? This means that s of z is analytic. If you have a function that, for which this is true, that its contour integral over every closed contour in some domain is 0, then this is Moreira's theorem, right? So s of z is analytic by Moreira's theorem. This is analytic by Moreira's theorem. Okay, so that's awesome. So let's restate that, right? So corollary of that first theorem, that's term-by-term integration from power series. The sum S of z of power of I should just say this power series. This is kind of confusing the way this is worded. So the power series S of z is analytic at every point interior to its circle of convergence. And why am I misspelling everything here? This is analytic at every point z interior to its circle of convergence. Okay. And so, yeah, right, this is kind of like a this is kind of almost like a, it's not really a converse-Taylor's theorem, but this is, you could think of it as like it's saying that the power series itself, right, is like when you consider it on a reasonable domain is analytic. Okay. We'll actually see that we can do term-by-term differentiation. Since we know it's analytic, right, then we know that we should be able to find its complex derivative, and so we're going to be able to do this by term differentiation of the power series. So let's do a quick example. So this is actually a nice way of showing some complicated functions are analytic. This is a nice way of showing some complicated functions are analytic. Okay, so what's the example here? So let's pick a function that is piecewise defined. So it's this f of z. So it is the function e to the z minus 1. Oh, not e to the here. It's e to the z minus 1 over z if z is not 0. And it's defined to be 1 if z is equal to 0. Okay, so it's e to the z minus 1 over z if z is not 0. And it is 1 if z is equal to 0. Okay. So what's the idea here? Note that e to the z minus 1 has a very easy Maclaurin series expansion. It's just the usual Maclaurin series for e to the z minus the first term, right, which is 1. So I just started n equals 1. So this is sum from n equals 1 to infinity of z to the n over n factorial. So that's easy enough. All right. Okay. So then if that's the case, then if I divide by z, well, let's just do that here. What happens? Okay, well, this is the same thing. I just, if you like, I have shifted, my index here. Well, I still sum from n equals 1 to infinity, but now I can write this as z to the n minus 1, if you like, over n factorial. Okay. All right, and so this thing is what? This is 1 plus z over 2 factorial plus z squared over 3 factorial, and so on. Okay. So notice that this is perfectly valid when z is not equal to 0, but also it's actually valid when z is equal to 0, right? Note, this clearly converges to f of 0, which is equal to 1 at z is equal to 0, right? Just plug it in z equals 0, it's clearly 1. They are just looking at the Laurent expansion. Okay. So then what does that mean, right? Well, the series converges to f of 0, which is 1 here, because you can literally just plug in z equals 0 here. Then otherwise, this seems like this would be a nasty thing here, but this is very clearly an entire function. This thing is analytic everywhere. It's analytic at z equals 0. Thus, f of z is represented by that Maclaurin series everywhere. So it is entire, because it's represented by the Maclaurin series everywhere, so it is analytic everywhere, because that Maclaurin series converges everywhere on the entire complex plane. So this f is actually entire. Okay. All right. In fact, right, we can actually just, if you're worried about what happens at z equals 0, note that since f is continuous, right, f is continuous at z equals 0. By definition, what does that mean? It means that the limit as z approaches 0 of f when it's approaching 0, so it's e to the z minus 1 over z is the form that f takes there. Well, this is the limit as z approaches 0 of f of z, but we saw that that's just f of 0. That's just 1, right? But rewriting this, right, we can say what's the limit as z goes to 0 of e to the z minus 1 minus 0 over z minus 0. What is that? That's just the derivative. So this is equal to e to the z minus 1, right, prime evaluated at z equals 0. So it's just the derivative of this thing is equals 0. So this thing exists. This is fine, right? So this is analytic at 0, so it's analytic everywhere. Okay, so it is an entire function. Okay, one more fact, right, about term-by-term differentiation. So term-by-term differentiation of power series. What do you get here? Well, I can compute s prime of z in the obvious way. This is just the sum. The constant term is going to drop out, so you're going to start at n equals 1 instead. The infinity of n times a sub n times z minus z naught to the n minus 1. I can just use the power rule here, right? Term by term. Okay. This might seem like kind of an obvious thing, and it's not. It doesn't require too much complication. In fact, you can actually prove this from the previous theorem involving integration. But this is a nice thing. In fact, let's do the following example. So in the following example, note that 1 over z, right, is the sum from n equals 0 to infinity of minus 1 to the n times z minus 1 to the n. Right, and this is valid when modulus of z minus 1 is strictly less than 1. Okay. So then if I take the derivative of both sides of this, okay, so if I start out with this identity and I take the derivative of both sides, then taking the derivative of the left-hand side, well, that's easy enough. That's 1 over z, minus 1 over z squared. If I take the derivative of the right-hand side by this thing that I've boxed here, this is the sum from n equals 1 to infinity of minus 1 to the n times z minus 1 to the n minus 1. And so actually I can rescale this if you like and multiply by a minus sign. So 1 over z squared can be written as the sum from n equals 0 to infinity of minus 1 to the n times n plus 1 times z minus 1 to the n, and this is valid on modulus of z minus 1 is strictly less than 1. So look, I actually was able to write this expression for, so I was able to write this expression for 1 over z. I was able to write this expression for 1 over z squared directly from this formula. All right, so that's pretty cool. Okay. All right. Now, a couple more facts here that basically are going to be important going forward. The other facts we need, I will use them as we need them. So I've already mentioned these a couple of times in today's lecture and in previous lectures. So here is the fact again. This fact is that these series representations are unique. Okay, so Taylor series, big fact. Taylor series and Laurent series are unique. What do I mean by that? Well, for Taylor series, we have the following. We'll call it Theorem 1. If a series, it is a power series, the sum from n equals 0 to infinity of a sub n times z minus z naught to the n, converges to f of z at all points interior to some circle, that's z minus z naught is equal to r, then it is the Taylor series expansion for f in powers of z minus z naught. Then it is the Taylor series of f. In terms of z minus z naught. Okay, that is expanded about z naught. Okay. Theorem 2 is same fact holds on annular domains for Laurent series. So this holds on annular domains. So, to restate it out, it means that if you have some series expansion, right, that kind of looks like a Laurent series, it actually is the Laurent series, right? So what makes the Taylor series the Taylor series? It's those funky coefficients, right? It's the fact that the coefficients are computed in terms of nth derivatives over n factorial, right? So we saw that in Taylor's theorem, right, that was not always the most convenient way of actually coming up with a Taylor series for a function. Sometimes just using basic algebra trickery was a quicker way of coming up with coming up with a Taylor series for it. So similarly for the Laurent series, as I mentioned before, in Laurent's theorem, right, there's those formulas involving contour integrals for computing those coefficients. But I mentioned to you in earlier examples that, in fact, every example we did today with Laurent series, we didn't use that fact to find the coefficients. In fact, we found the coefficients, and we used this fact that, oh, it must be the Laurent series, right, that I'm stating now, to actually show that those contour integrals had to be equal to the coefficients we had already found in some other way, right? So we had that what makes something a Laurent series specifically is that, oh, those coefficients are computed like this. But hey, it turns out that really what makes a Laurent series is just the fact that it looks like a Laurent series, right? It splits as, it's a positive part, it's the positive like power series part, and then it's the power series except with negative powers part. Okay, and so if you come up with any kind of series representation for your function, it looks like that, and it converges at every point in some annular domain, then it is the Laurent series there. And so you can say use any way of finding it, like we did in the earlier examples, where we did a bunch of examples of Laurent series. You can use that to find it, and then you don't have to compute those contour integrals. In fact, you can use the Laurent series that you found to compute those contour integrals backwards, basically, is what you're doing. Because you're saying, oh, I found these coefficients, and now I know by Laurent's theorem that those coefficients have to be equal, to those contour integrals. So that's the deal. And so that's really nice. That's a really nice fact. Okay, and so now what we wish to talk about next. So the roadmap for the last few lectures. One, we want to talk about singularities. So we want to talk about isolated singularities. We want to talk about what we're going to call poles. We want to talk about essential singularities. So we're going to talk about all those. Okay. Next, we want to talk about residues and the residue theorem. And then last, we want to apply the residue theorem. To get beautiful results, right? That's the goal. That is the hope. That's the dream. All right. And so, in order to start this process, let's talk about isolated singularities, or isolated singular points. Okay. All right, so what are these? Now, note that Cauchy-Gorsat tells us that if f is an analytic function, at all points interior to and on, a simple closed contour C then the contour integral over C of f of z dz is 0. Okay, so we already know the answer. Right. But what happens if this fails at a single point? But what if f of z is not analytic at even a single point in the interior of C? Well, what happens is that this integral is not 0. Okay. This integral can be all kinds of things. We saw, go back and look at the examples of when we computed the contour integral of 1 over z. Okay, that showed a great illustration of what can happen when you have a single point. Right. So if you had a contour, simple closed contour that encircled the origin, right, and you wanted to integrate 1 over z over that contour, you didn't get 0, right? If you had a simple closed contour that actually missed the origin, didn't enclose it, then actually you get 0 by Cauchy-Goursat, okay? So then enclosing a single bad point leaves behind some value, okay? It leaves behind what's called a residue, okay? These points contribute residues, okay? And so such a point contributes a residue to the contour integral of f. Okay. This is the idea. And so the idea is that by the time I state the residue theorem, you are going to be able to compute these sensible contour integrals over regions where f is analytic, except at some finite set of points where it is singular. Okay. And you're going to do this in terms of the residues at those points, because nothing else is going to matter, only the residues are going to matter. That theorem that we went over way back when we first talked about Cauchy-Goursat that dealt with multiply connected domains, that picture is really good for understanding what it is that goes on when we look at regions that are going to be described like this. Okay, so remember, we need some terminology here. Remember, a point z0 is called a singular point, or singularity of f if f fails to be analytic at that point. Okay, that's it. Simple as it is. Okay, so it fails to be analytic at z0, but okay, is analytic at some point in every neighborhood of z0. At some point in every neighborhood of z0. Okay. So that's a singularity. An isolated singularity of f is a singularity of f. We'll call this isolated singularity z0. So an isolated singularity z0 of f is a singularity of f such that there is a punctured disk that is given by modulus of z minus z0 is strictly between 0 and, say, I used delta here, I meant epsilon, Freudian slip. Okay, such that there is a punctured disk on which f is analytic. Okay, isolated singularities are going to be what we'll refer to kind of casually as nice singular points or nice singularities. Okay, so what is the idea behind an isolated singularity? Okay, an isolated singularity, easiest example of one is the singularity of 1 over z, right? 1 over z has an isolated singularity. It's a singularity z equals 0, right? It's the only place it fails to be analytic. It's analytic everywhere else. Okay, so let's look at an example here. Right, so let's look at the function f of z, which is, say, z plus 1 over z cubed times z squared plus 1. Okay. What are the isolated singularities of f? So isolated singularities of f, or all of the singularities of f. So isolated singularities of f are the points z equals 0 is an isolated singularity, and z equals plus or minus I. So it's got 3 isolated singularities. There they are. Okay, they're exactly what you think. Why are they isolated? If you actually drew the points, right, where there are issues here, what do they look like? Where's this thing not analytic? It only fails to be analytic by the quotient rule, right, if you like. This only fails to be analytic here and at plus I and minus I, right there. Those are literally the only 3 holes. Everywhere else it's analytic. Go back and look at that condition of being an isolated singular point. Those are definitely isolated. Okay, look, boom, there's a punctured disk in question. There's the one about that one. There's the one about that one, right? Okay. All right. Well, let's see examples of singularities that are not isolated, right? What's the first thing we're going to think of? Right? Let's let f of z be principal branch of log z. Right, so this is just to refresh your memory, right? It's been a while. Natural log of little r plus I times the principal argument, big theta. So the cut that I've taken, so r is strictly greater than 0, and theta is strictly between minus pi and pi, right? Okay. So, of course, you can take any point along the branch cut here as a singular point, but let's just look at the origin, right? The origin is a singular point. So the origin z equals 0 is a singular point of f of z. Actually, it's a branch point, which is necessarily a singular point, but actually branch points are even worse than, say, an isolated singularity. Branch points are going to be real bad, right? Because this branch point is a problem on every branch, right? So branch points are actually nasty. They're one of the nastier types of naughty points, right? It's not isolated, right? But the singularity is not isolated. So the singularity at z equals 0 is not isolated. Why? Why is it not isolated? Well, let's draw up, right, what does this look like? This has a stupid branch cut on the negative x-axis, right? This has a stupid branch cut here. I'll do the thing I always did before. Here's my stupid branch cut, right, on which this function is not well defined. Here's what my region looks like. What's the problem? Problem is that if I look at any neighborhood of the origin, it contains the stupid branch points on the branch cut. Right? There's no getting around it. Any neighborhood, no matter how big or small, is going to contain points on the negative x-axis, which is a branch cut for this thing. Okay, so it's not isolated. Okay, this is an example of a bad singularity, right? This is bad. It's a branch point. Okay. So we are going to see very quickly what types of singularities we want to deal with and how we can deal with them. Okay. And so we're going to be happy with isolated singularities. We're going to be happy with poles, okay, which are a particular type of singularity that we'll discuss when we talk more about this stuff and when we talk about the residue theorem. So now we're in position to basically, I'm going to do a few more examples on Monday, and then I'm going to immediately state the residue theorem and go full force on doing examples and applying this stuff. So you're going to have a midterm. Like I said, it's going to be assigned over the weekend. It's going to involve it's going to be mostly like the homework. It's going to involve some conceptual stuff, since it's covered, since first midterm, it's going to cover a lot of stuff we did, like we did Cauchy-Gorsat and all kinds of cool things with contour integrals that allow me to ask questions that are conceptual, that are also not too hard, too crazy difficult. Because some of these questions are, even a very simple question like coming up with a good example of, for instance, a function that satisfies Cauchy-Riemann but it's not analytic somewhere. That's kind of an involved counterexample you have to come up with. It's not easy. I wasn't able to come up with one off the top of my head. So stuff like that, I'm going to shy away from. I don't care about that. But there are plenty of fair conceptual questions I can ask you about contour integrals, and that's some of the stuff I'm going to do. You're going to have homeworks next week that are going to focus. So you already have a homework that I assigned. It's basically just a refresher on dealing with power series. And then next week you're going to have homeworks on residue theorem and applying some of the stuff that we're doing in these last lectures. And then at the end, you're going to have your final, which I'm going to just kind of include a smattering of all kinds of stuff and maybe some questions that I left off of previous exams or homeworks, okay, that are complementary. So that is the deal. And so the reason why this became a combo lecture is because I thought it kind of worked out better. Like that, to kind of tidy up this remaining material from that block of stuff so that we could go full force into residue theorem stuff, which is what I'm going to start on Monday. So I want you guys to have a good weekend. Let me know if you have any questions. On Monday, I will hold office hours again. So 2 to 3 is when they'll be, the usual time. And so I will see you all in lecture on Monday. So have a good weekend and have fun.